Saya Muhammad Rafiq Safwan 220024 akan memulakan pembentangan bagi projek untuk Computer Organization dan Architecture. Saya akan mulakan bahagian saya bagi projek ini, iaitu berkenaan dengan disk transfer. Disk transfer ini adalah the exchange of information antara user dan juga CPU. Cara user exchange information CPU adalah melalui I/O ataupun input output devices yang akan communicate dengan memori. Ada tiga cara untuk disk transfer ni berlaku, iaitu program I/O, interrupt driven I/O, DMA ataupun direct memory access, yang akan saya terangkan dalam pembentangan saya. Yang pertama adalah program I/O. Kita rujuk kepada flowchart ni. Flowchart ni akan menerangkan bagaimana proses program I/O tu untuk transfer data. Yang pertama, CPU dia akan issue command kepada I/O module, issue read ataupun write command kepada I/O module, dan dia akan check status sama ada I/O module tu dia dah ready atau tak untuk menghantar ataupun menerima data. Sini kalau dia belum ready, dia akan keep on rechecking sehinggalah I/O module tu kata dia dah ready untuk accept ataupun hantar data. Bila status I/O module tu dah ready, berlakulah pertukaran data, iaitu read ataupun write word daripada input I/O ataupun memori. Kalau masih ada lagi data yang ingin transfer, proses tu belum habis lagi, maka dia akan mula balik pada atas ni lah. Dia akan keep on repeating sehinggalah dah habis. Kalau proses tu dah habis, maka dia akan teruskan dengan next instruction, pergi ke arah yang seterusnya. Itu menerangkan macam mana program I/O ni dia melaksanakan the transfer of data. Kelebihan untuk program I/O ni adalah dia simple untuk implement dan dia memerlukan very little hardware support. Tapi disadvantage dia adalah dia busy waiting, ties up CPU for long period with no useful work. Maksudnya tadi kan kita rujuk balik pada flowchart ni, CPU dia harus menunggu I/O module tu. Sebentar dia menunggu tu, dia tak boleh nak buat apa-apa. So that is why dia macam dia tak ada benda untuk dia buat. So macam membazir waktu begitu saja. Next adalah interrupt driven I/O. Kita rujuk balik kepada flowchart ni. Dia akan menerangkan bagaimana interrupt driven I/O tu melaksanakan the process of transferring data. First, CPU dia akan issue read command kepada I/O module. Dia akan issue, kemudian CPU tu dia akan do something else. Dia akan buat kerja lain. Macam tadi, CPU akan keep on rechecking status dia, tapi sini dia menghantar issue command tu dan CPU melaksanakan tugas yang lain. Bila I/O module tu dah ready, dia dah ready untuk accept ataupun menghantar data, dia akan menghantar interrupt signal kepada CPU untuk memberitahu yang I/O module tu dah bersedia untuk menerima ataupun menghantar data. So sini dia akan check balik status tu, dan bila dah ready dan berlakulah transfer of data, read ataupun write word daripada I/O ataupun memory. Dan kalau proses tu belum habis, maka dia akan keep on repeating balik this whole process yang dalam flowchart ni. Kalau it's done, dia akan proceed kepada next instruction. The advantage of interrupt driven I/O ni adalah dia fast dan efficient. Kenapa dia fast dan efficient? Sebab setelah dia nak tunggu I/O module tu, dia akan buat kerja lain. Maksudnya CPU tu dah tak membazir waktu macam tu. Dia boleh buat kerja lain. Dia macam multitasking gitu. So dia cepat dan dia lebih efficient. And the disadvantage of interrupt driven I/O ni, dia akan be a bit tricky to write if using a low level language, and juga tough to get various pieces to work well together. Seterusnya adalah DMA ataupun Direct Memory Access. Perbezaan antara yang kedua tadi, yang first tadi program I/O dan juga driven interrupt I/O, DMA ni dia peranan CPU ni dia kurang. sebab dia akan directly access antara memori dengan disk. Sini with DMA, ni without DMA. Kalau without DMA, macam first saya kata, ia akan melibatkan CPU punya peranan lebih besar. Kita tengok balik kepada flowchart ni. Okay, flowchart ni dia issue read block command kepada I/O module. Maksudnya dia ada issue command kepada DMA module. Maksudnya CPU sini bila dia ada command untuk read ataupun command kepada I/O module tu, CPU ni dia pass control tu kepada DMA. DMA require control on system. So bila I/O ni dia ada nak transfer of data, kan, CPU ni dia pass control tu kepada DMA, CPU ni buat kerja lain. Jadi DMA ni dia yang akan control the transfer of data antara memori dengan external devices. So sementara CPU buat kerja lain, DMA yang handlekan the process tu. Sebab dia yang ada control on the system. Bila transfer of data antara memori dengan external device tu dah complete, then DMA dia akan send signal kepada CPU. Sini dia akan hantar balik signal untuk interrupt kepada CPU. Dia akan beritahu balik kepada DMA, dia akan beritahu CPU yang proses penghantaran data antara memori dan external device dah complete. Then dia akan proceed kepada next instruction. Okay, itulah flow dia, macam mana direct memory access tu berlaku. Okay. The advantage of DMA adalah dia allow peripheral devices to read and write to memory tanpa melalui without going through the CPU. Okay, ini membenarkan untuk faster processing since the processor can be working on something else while the peripheral can be populating memory. So dia lagi cepatlah proses the transfer of data tu. And the disadvantage adalah requires a DMA controller to carry out the operation, which increase the cost of system. Maksudnya cost of system tu akan lebih mahal lah sebab dia memerlukan DMA controller. Next disadvantage dia adalah cache coherence problem. Okay, itu saja. Saya dah menggunakan ketiga cara bagaimana disk transfer berlaku. So, saya akan memberi ruang kepada rakan sekumpulan saya untuk melaksanakan bahagian seterusnya untuk projek computer application ini. Okay, terima kasih.
Assalamualaikum. My name is Huzaifah bin Hamzah 2200277, and now I will continue this presentation. Okay, now I will explain about internal memory and I/O address spaces. Okay, processor memory is accessible in 8, 16, 32 and 64-bit quantities, while processor I/O is accessible in 8, 16 and 32-bit quantities. This processor can directly address up to 4 GB of physical memory, while for I/O can up to 64 KB. In hardware, memory space is organized as a sequence of 64-bit quantities. Each 64-bit location has 8 individually addressable bytes at consecutive memory addresses. As you can see, there is 80 as the consecutive memory addresses, and each 0 there is 8 individually addressable bytes. So 8 times 8 mean memory space has 64-bit location, while for I/O address space it has 40. It means there is 4 consecutive memory addresses, and each 0 has 8 individually addressable bytes. That means 8 times 4 equals to 32-bit location that contain in I/O address space. Okay, now we will move on to this figure. This figure is a bus cycle. What you can see from left to right, this is what we call bus cycle. And for the first row CLK, which is clock, this is the clock cycle. And for the rest, what you can see, the line is what we call signals. Next, I will explain about the components at the row and columns. Okay, for the column, T1 means the first clock of a bus cycles, and T2 is the second and subsequent clock of the first outstanding bus cycles which occurs in T1, and Ti means bus idle state. In this state, no bus cycles are being run. Okay, for the each interval, which is vertical dash lines, is a clock cycle. As you can see at the first row, CLK is main clock, and the signals right to it is the clock cycle, while the entire flow from left to right is bus cycle. The bus cycle is the time taken to complete a single read. To understand the signal lines, when you see the signal line is going up, it means read. It means write. And when you see the signal line is going down, it means read. And when you see the line is constant straight for a long period of time, it means it is idle or hold. For the second row, ADDR, it means address. During a period in T1, when there is a valid address, status are driven out, and ADS hashtag, which means address rope, is exerted. And during this period too, there is one outstanding bus cycle. What is one outstanding bus cycles? Okay, one outstanding cycle indicates the number of catchable read bus requests that are outstanding in any cycles. I will explain about the ADS later. Okay, now during T2, if the cycle is a write, data is driven out. And if the cycle is read, data is expected and the BRDY hashtag pin is sample. And there is also one outstanding bus cycle. And you can see when the bus is in idle state, there is no address driven out, so it is invalid. And for this for the next cycles T1, the address back to valid because there is a valid address and status are driven out. Okay, now for the third row ADS, which as mentioned before. Okay, ADS or address drop is the processor initiates a cycle by asserting the address status signal in the first clock. The clock in which ADS is asserted, by definition the first clock in the bus cycle. The ADS output indicates that a valid bus cycle definition and address is available on the cycle definition pins and the address bus. For the cache hashtag, or before that, this hashtag indicating an active low signal. Okay. For the cache hashtag, the cache output is deasserted to indicate that the cycle is a single transfer cycle. So when there is a valid address, it will write and the process will end when the data status are driven out completely. Next, read write hashtag. Read write is one of the primary bus cycle definition pins. It is driven valid in the same clock as the ADS hashtag signal is asserted. Read or write distinguish between write and read cycles. Next is BRDY hashtag. It has been mentioned once before. Now I will explain what is BRDY hashtag. BRDY hashtag indicates that the external system has presented valid data on the data pins in response to a read, or the external system has accepted data in response to a write. So it occurs when the data is being read or write. So the memory subsystem returns BRDY when the current transfer is complete. For non-burst transfer, a single BRDY is returned, completing the bus cycles. After asserting ADS hashtag, the microprocessor samples BRDY in the second clock cycle after driving out ADS, so that the first transfer takes at least 2 clock cycles. If the address hits in the cache, the bus transfer will be completed and BRDY return in this clock cycle. And lastly, for the data, the first cycle T1, T2 is driven out to the CPU, and for the second cycle T1, T2 is from the CPU to be processed and end the bus cycle completely. Last but not least, for the standard Intel Pentium read and write bus cycles, computer system performance could be improved by reducing the number of clock cycles to complete a non-burst cycles. In particular, current cache performance is such that depending on speed of the local bus, the cache will be able to detect ADS, perform cache lookup, and signal a hit in the same clock cycle as the ADS. Next is Intel Pentium burst read bus cycle. For bus cycles that require more than a single data transfer cacheable cycles and write back cycles, the processor uses the burst data transfer. In burst transfer, a new data item can be sampled or driven by the processor in consecutive locks. In addition, the addresses of the data items in burst cycles all fall within the same 32 bytes aligned area. The implementation of burst cycles is via the BRDY pin. While running a bus cycle of more than one data transfer, the processor requires that the memory system perform a burst transfer and follow the burst order. In this figure, data is sampled only in the clock that BRDY is written, which means that data need not to be sent to the processor every clock in the burst cycle. As we can see, the occurrence of T2 on the clock cycle is 4 times, which means the data is driven out 4 times faster than usual standard Intel Pentium. And lastly, for the Intel Pentium hold acknowledge bus cycles. This occur when the bus is in hold or idle condition. The embedded Pentium processor provides a bus hold acknowledge protocol using the hold and HLDA pins. Hold is used to indicate to the processor that another bus master wants control of the bus. When the processor completes all outstanding bus cycles, it releases the bus by floating its external bus and drive HLDA active. We can see that the address is valid starting at the T1 and at the T2, and starting the TI, the address is hold until the next cycles. It is hold because of there is 4 TI, the bus idle, and during that phase, no address will be driven out. Same goes to the ADS, cache, read and write, BRDY, and data. Note that hold may be acknowledged between 2 bus cycles in a misaligned access. That's all from me. We will proceed to the next presenter. Thank you.
Good morning, ma'am. I'm Chong Xin Yin, matrix number 2200275. So today, I'm going to talk about encoding. So encoding is the process of converting a data from one form to another form, which is into the signal form, because we cannot transmit a data until it is converted into a signal form. And for the data in the signal form, it can be in digital or analog form. So there are also many types of encoding, which is image encoding, audio encoding, video encoding, and character encoding. So encoding of electronic devices like computers, the data encoding involves certain coding schemes that are simply a series of electrical patterns which represent each piece of information that need to be stored and retrieved. So for example, a series of electrical patterns which represent the letter A in ASCII table. So the data encoding and decoding occur through the electronic signals or the electric or electromagnetic encoding of data. So during data encoding, all the data is serialized and they need to convert into a string of 1 and 0s because computer system only read number 1 and 0s. So let's see what is a digital signal. So a digital signal is a signal that is being used to represent data as a sequence of discrete values. And at any given time, it can only take on at most one of the finite number of values. While analog signal is one type of continuous time-varying signals, and it can be classified into composite and simple signals. So a simple type of analog signal is nothing, but it is just a sine wave, and it cannot be decomposed. Whereas a composite type of analog signal, it can be decomposed into numerous sine waves. So here is an image that we can clearly see the difference between digital signal and analog signal. So as we read just now, the analog signal is a combination of a few sine waves, while a digital signal is just in a signal form. So next. So here is an image that we can differentiate clearly between encoding and decoding. So as we can see, encoding, it is just the number of 1 and 0s, while decoding is we decode these values into the words that we can read, like we had learned in the previous chapter about about decoding. So this is an image that we can differentiate the encoding and decoding easily. So in this chapter, we're going to focus on Nrz encoding and Manchester encoding. So the full name of Nrz encoding is non-return to zero encoding, and it is used in the slow speed synchronous and asynchronous transmission interfaces. So with Nrz encoding, a logic 1 bit is sent as a high value and a logic 0 bit is sent as a low value. So this is an example of Nrz encoding. As what I said just now, the logic of 0 bit is sent as a low value and the logic of 1 bit is sent as a high value. And as we do like this, we can get a signal form of the Nrz encoding. And Manchester encoding is a synchronous clock encoding technique that used by the physical layer of the open system interconnection to encode the clock and data of a synchronous bit stream. So the Manchester code is a line code in which the encoding of each data bit is either low then high or high then low for the equal time. So this is the example of the Manchester encoding. And as we can see, the 0 represents the line bit like this, which is high then low, while the 1 is low then high. So for the simple understanding, we can expect that the 0, the high value of 0 is on the left-hand side, while the high value of the logic 1 is on the right-hand side. So we can understand this more easily while we are doing, as we just draw the high value for 0 on the left-hand side and high value of 1 on the right-hand side, and we can get the signal form of the Manchester encoding. Next. Okay, so here's an exercise for we to revise that we can make sure that we understand what is encoding. So the question given is 4F in base 16, and we need to convert it into Nrz encoding and Manchester encoding. So before we do the encoding, we need to convert the base 16 into base 2 by using this method, and we get the value 1001111. So for Nrz encoding, we knew that the high value for 1 is the 1 is on high value and 0 is on low value for Nrz encoding. So we can get this answer. While for Manchester encoding, the high value of 1 is on the right-hand side and the high value of 0 is on the left-hand side. So 0 left-hand side, 1 right-hand side. So we can get the Manchester encoding of signal form. So that's all from me. Thank you.
Nrz232 ialah alat yang digunakan untuk menyambungkan komputer dengan peranti lain. Penyambung yang biasa kita gunakan 9 pin dengan 25 pin. Ini sedikit sejarah tentang Nrz232. Mula diperkenalkan pada tahun 1962, kemudian dikemas kini oleh Electronic Industry and Alliance. Ini gambar wajah tentang male DB9 connector dan female DB9 connector. Gambar wajah ni pula tentang penerangan pin dan dia punya jenis-jenis dia. Gambar yang seterusnya menunjukkan spesifikasi Nrz232. Jadi bolehlah baca-baca, fahamkan. Jadi kelebihan Nrz232 ni, dia banyak peranti yang boleh support dia. Yang kedua, dia punya boleh panjang sampai 50 kaki. Yang ketiga, dia kebal terhadap gangguan bunyi. Yang keempat, harga dia murah. Kita ke slide seterusnya, kekurangan dia. Jadi kekurangan dia tak sesuai pada peranti yang mempunyai sensor, dan juga dia memerlukan interface yang berlainan yang mana akan menambahkan kos. Jadi kita teruskan dengan USB dan Firewire. USB adalah singkatan ringkas kepada Universal Serial Bus, mana nama saintifik bagi Firewire ialah IE1394. Ini memang tak dapat nafikan Firewire lebih cekap kerana boleh dapat capai 800 Mbps. Perbezaan yang utama antara Firewire dan USB. Jadi persamaan mereka dapat pindahkan data dengan cepat, tapi Firewire lebih pantas daripada USB. Contoh 2.0 USB hanya boleh memindahkan 450 Mbps, manakala 800 Firewire dapat memindahkan 800 Mbps. Walau bagaimanapun, USB 2.0 dapat manage 120 device berbanding dengan 800 Firewire yang dapat hanya manage 63 device. Persamaan dia dua-dua ni ialah menggunakan plug and play, di mana bila kita masukkan peranti ke dalam komputer, yang saja persembahan presentation daripada saya. Semoga bermanfaat untuk semua. Sekian, terima kasih.